Hello there, algebra students and YouTube math wanderers. We're here today to talk about complex numbers in a continuation of our work with roots and radicals in algebra. So complex numbers are an important topic with many applications in like electricity with AC circuits and in fractal geometry. So it's a very fascinating topic. So we're going to start with the basics. And we'll define what a complex number is and how it includes imaginary numbers, and we'll look at the definition of imaginary numbers and ways of working with them. So stay tuned. We got a lot to cover today, and with some good examples following. So first off, what we want to do is we want to think about the challenge that we ran across previously. How do we work with even roots or radicals where the index number is even, where this is a square root or a fourth root, when you have a negative number or a negative value underneath there in general. So can we take the square root of -1? Well, previously we'd say, no, that's not a real number, and we'd stop. So in the world of applications, in the world of math, we need to be able to invent a system where we can actually work with these. So that's where the complex numbers came from. Instead of saying stop, we can't do anything further, we came up with a definition of working with, a definition, a system of working with negatives under even roots. Okay, so what we know is that these are non-real examples. Okay, previously we'd say these are not real. And if you remember our symbol for real numbers, it's this. These are not real numbers. Okay, so what we do is instead we say, and bear with me a little bit, we're going to make a foundation of definitions and tools that we'll use in our problem solving. So the idea is, since the square root of -1 is not a real number, okay, I'm going to choose this number symbol for short for number, is not a real number, a new system of numbers. The complex, we're going to introduce the complex number is introduced to work with these. With the nth root, even roots of negative values. Okay, where this is an even root. So let's talk about the complex number system. So the complex number system is a number system that's much bigger than the real number system. It includes the real numbers, but it also includes the imaginary numbers. So the complex number system uses an imaginary unit by definition, we have a lowercase I, which is equal to this value of the negative square root of 1, the square root of -1. So what we're going to do is we're going to say, instead of stopping with a square root that has a negative under it, we're going to say, well, let me say that this I, this imaginary unit, is equal to the square root of -1. And let me proceed with my rules of algebra to be able to work with problems with these negatives under the roots. So this is a very important definition. We're going to define this imaginary unit, which is part of the imaginary numbers we'll talk about. This imaginary unit which is an imaginary number, which is part of the complex number system. So we're going to use this definition, and we're going to say further that if we square this, if we say I squared, if we say I times I, which is the square root of -1 times the square root of -1, we get the value -1. Okay, there's a basic rule there. Okay, so our complex number system are going to use these imaginary components, these imaginary units. So here is just a basic outline of the complex number system. Complex numbers, they have many applications. So apps is short for applications. We have electricity. It comes up in AC circuits, the fluctuation of the current. We use it for current values. Electricity, fractal geometry. So there's different applications in geometry. I'll just say geometry for short, etc. Those are the main ones I'm familiar with. But the big idea is whenever it comes up in any problem solving, when you have the negative, the complex number system is a way of working with those negatives under roots. Okay, so the complex numbers is really important. And what it does is, here's a general diagram. I'm going to do a diagram of how these sets work. So let me say this is the universe of complex numbers right here. All complex numbers possible, which is a lot. So obviously they can't be contained in all this box, but this is just a little pictograph here. We have complex numbers, universe, and inside complex numbers we have the entire set of real numbers. So inside this we have real numbers, and if you remember, real numbers include, this is the universe of real numbers, and inside the set of real numbers you have the set of rational and irrational numbers, right? So real numbers, you have the rational numbers in here, which are all the numbers you can make into fractions. Inside that set you have the integers, whole numbers, natural numbers, and of course the sets get smaller and smaller. So I'm going to say ... all these little mini universes. So rational numbers is a smaller number set than the real numbers, which is a smaller number set than the complex numbers. So there's a lot of numbers in here. So rationals plus irrationals here. Here's the outer parts of the universe where the irrationals, the ones that don't form fractions, live. So this goes on to integers. Since this is on camera, I know you can zoom in, and of course it gets smaller in there. So the complex number universe is an infinite number of, there's an infinite number of complex numbers, which is and there's an infinite number of real numbers contained inside the complex number, and there's an infinite number of rational numbers contained in the real number system, etc. So just to give you a general idea. So let's go ahead. So this thing, all complex numbers include real numbers. I'm just going to emphasize that point here. Okay. And some other important details to address and to form your foundation in working with complex numbers is to look at this complex number form we're going to use. Okay, so the next thing we want to address is this complex number form. We have a certain way of writing all complex numbers, and the template is A plus bi. So this is how we typically write any complex numbers. We write the real number part first and then the imaginary part. So what we have is, we have our real number part here. And sometimes that might be 0. And here we have our imaginary number part. Right here. And of course we have I, which is defined as the square root of -1. Very important. So we have all these little parts that make up our complex number form. So here are some examples. Okay, so here's an example of a complex number. Let's say just 2 plus 3i. Okay, it almost acts like an x. It's like saying 2 plus 3x, except that we know what I is. You know, x is just a variable of unknown value. Here we actually know what the I value is. It's just the square root of -1. So you can see here that you have your real number part, and here you have your complex or your imaginary part. So the real number part plus the imaginary number part equals your complex number. Bingo. Okay, what if you have just an example like 5i? What happens here? Well, that also is a complex number. If we write it in complex number form, what we have is, we have 0 plus 5i. Okay. What we recognize is that the real number part is 0. So here we have our real number, and there's our complex number. Okay. So any other examples we could provide? Well, what about if you have just a number like number 3? Let's go ahead and say we have something like just the value 5 in this case. Okay, is that a complex number? Yes, every real number is a complex number, but not every complex number is a real number. So very important on how you read these diagrams. So there are different number sets. These are sets within sets. So here we have in our case here, we only have the real number part. So if we write this in the a plus bi form, in complex form, we're going to say 5 plus 0i. And that would be our answer in complex form. Okay, I'm going to circle these so that this is in complex form, 0 plus 5i, and 5 in complex form is 5 plus 0i. There's 0 imaginary to it. Okay, so those are some basic examples. Now, let's go ahead and define something called the complex conjugate, and then we'll work with a few simple examples, and then add in some other interesting features of complex numbers based on the definition that we could apply. So we have something called the complex conjugate, and we work with this a lot because a lot of times we don't want, just like we don't like to have square roots and denominators, we don't like to have imaginary parts and denominators. So let's go ahead and take a look at the complex conjugate, which is something we're going to work with. Something we're going to work with to make sure we're not left with any algebraic expressions that have I in the denominator. So the complex conjugate is if you have a complex, let me back up, I'm going to rewrite this, given any complex number a plus bi, the complex conjugate is a minus bi. Okay? So if you have a complex number that's a plus bi, then the actual conjugate will be the same real number part, but opposite in sign with your imaginary part. So compare these two. This is called the complex conjugate. And what we do is we use this, we convert to a plus bi form, and then any i's that we end up with the denominator we'll get rid of with the conjugate. So this is going to apply to eliminate the bi or any I terms from the denominator, from the denominators. If you have, this is where we're going to apply this, okay? Upcoming. So now the next important thing is we defined all our basic introductory ideas with complex numbers. And now what we want to do is work with our operations. We want to look at operations with complex numbers. We want to be able to add them, subtract them, multiply them, and divide them. Okay, and eliminate i's from the denominator. That's going to be part of the division part. Okay, so what we're going to do is we're going to look at these operations with complex numbers. We're going to do that, but we're also going to look at simplifying. We'll look at some general I expressions that we could simplify. Okay, so now let's go ahead and start with some very quick examples. And then I'll go more into the operations. So let's first look at just simplifying. Simplifying with complex numbers. Okay? The main idea convert -1 negatives to i's. Okay. What we're going to do is convert any negatives to i's, simplify the radicals. I'm going to leave out the index number for now. We're going to simplify the radicals. And the next step we're going to do is reduce any complex number that has an I exponent greater than 1 to the power 1. So convert I to a greater power, where n to a lower exponent. Okay, so we're going to come back to this part right here. Okay, those are going to be our main ideas in simplifying, and then we're going to go ahead and look at doing more with operations and simplifying. We're going to start simple, start out small. Okay, so let's start with a problem that says simplify, and we have, let's say, the square root of -25. Okay, so instead of saying this is not a real number and we're blocked, we can't do anything more with the problem, what we're going to do is we're going to break it up into complex number form, break it up into I form. So the first thing we want to do, use the square root of -1 definition. I'm going to break this down into, well, this is the same thing as, this is a square root, my index number is a 2. So I'm going to break this down to -1 times 25. So that I can represent that -1 with an I. So the next step would be to say, this is the same thing as saying the square root of -1 times 25, square root of 25. Okay, and when I break it down like this, I could represent the square root of -1 with an I, and this becomes I times the square root of 25, which is just 5, luckily for me. And according to the template I use for a complex number form, I don't leave I times the I on front, even though we know I times 5 is going to be the same thing as 5 times I, just like x times 5 is the same as 5 times x. In this case, what I want to do is go ahead and reverse this and say 5i. It's easier to write that way. And it's in line with my complex number form. So that's how I work with simplifying a radical like this. Okay, some other ones that I want to look at. Let's go ahead and do another practice problem. Why don't we go ahead and do the 4th root of a -81. Okay, here's an even root. How would I work with this one? Well, what I do is I can't take the even roots of negative numbers again, so I need to somehow extract my complex number out of there. So what I need to do is make this the -1 times the square root of, times the 4th root of -81. So the 4th root of -1 is also going to be -1. So because we have the -1 power, we know the square root of a 1 is 1, the 4th root of 1 is 1, the 6th root of 1 is 1, etc. So we're going to apply a little trick here, and using that definition, we could go ahead and say the 4th root of -1 is also going to be I by the same arguments. And we could say I times the 4th root of 81, which is what number multiplied by itself 4 times gives you 81? Well, that's that's 3 times 3 times 3 times 3, or 9 times 9, and we get 9i out of this. We had a little bit of a jump here, but it works out the same way. For the most part, we'll be sticking with square roots. What if we have something like step here. Your second or your last is always to make sure this is in complex number form. I'll emphasize that some more too. Just a quick little add-in thought as I was going along there. Okay, apply your definition, make sure your final answer is in complex number form. Let me fix this so it looks a little little better. So that's what we did here and here. So let's take another problem. And let's see if I had something like the square root of negative 72. How would I simplify that? Again, instead of saying, well, I can't do anything with this because it's not a real number, I'm going to apply my definition of the imaginary unit and what an imaginary number is. And I'm going to apply my operations I learned previously, my definitions previously as well, on square roots to simplify this. Now, we notice that 72 is not a perfect square, so I have to break it down into parts where there are factors, pieces of 72 that are. So I'm going to break down a lot here. I'm going to break this down into the negative 1, which is the imaginary unit, times 72 is the same thing as 36 times 2. I look at pieces that are perfect square of 72, so I'm going to say 36 times 2. And it looks like that will work for this problem. I could simplify a lot of this radical. So now, writing this out in individual roots, this is equivalent to the previous expressions. And I can now write this as I times 6 times the square root of 2. So altogether, I have 6. And where should I write the I? I like to keep my front coefficient way out in front. And the convention is to keep the i's in front of the square roots so that they do not get confused with being under the square root, because that's illy defined. That just doesn't work in the world of math. So that would be our final answer. So here we have this in complex number form. I could go ahead and say 0 plus 6i square root of 2. But it's not always necessary to write the 0 there. So here we have our complex number. Okay, so the next step here is to look at some other numbers with combinations. Let's say we had 4. Let's say we had something like this. Well, same idea. We simplify this and we say 6 minus, and we could break down this minus 50 to negative 1 times 25 times 2. And this becomes 6 minus 25 comes out as a perfect square. It becomes 5. Negative 1 comes out, that's an I. This becomes 5i square root of 2. And now you have your complex number form. You have your real number part and your complex part. Excuse me. You have your real number part and your imaginary part, which equals your complex number form. Okay. I'm going to get to something like that has a really high exponent for I we haven't dealt with. So let's go ahead and say, let's go ahead and look at powers. And here's a question for you. How to simplify something that is like I to the 10th power. Wow, okay. How do we work with something like that? Maybe we end up with more than one I if we're, you know, working with different multiplication of roots. We have a lot of multiplication of roots involved. So here's a little pattern to know and work through. Okay. And the idea is when we have any power of I that's greater than 1, we break it down. So if we start with I, and I'm going to go ahead and say I by definition is defined as a square root of negative 1, and the symbol we reduce to just the I value. Okay. If we have an I squared, remember that's a -1 square root times a -1 square root, or basically an I times I the first power times I the first power, and that really is just the value -1. So if you ever see an I squared in an expression, you replace it with the number -1. What about an I cubed? Well, let's break down the exponents of I cubed. That becomes a I squared times an I. Now I squared is a -1 times an I. So this whole thing we reduce to a -I. And what about an I to the fourth? Well, an I to the fourth power is just an I squared times an I squared. And as you might see, I squared times I squared is -1 times -1, which we represent just with a 1. So any I to the fourth power we replace with a 1. Any I cubes we replace with a I squared with a -1. I is just I. Reduce, replace with one of these 4. Okay, now how do we address the I to the 10th power? Well, the idea is any of these higher exponents can break down to one of these components. So we have to know these. We have to know that I is I squared is -1, I cubed reduces to -1, I to the fourth reduces to 1. And no, you don't have to absolutely memorize them, you could always break it down. But this is what you want to reduce these powers to. So any I to a power of n, where n is greater than 4, we want to reduce by factoring out the highest multiple of 4. So the trick is to take out the highest multiple of 4 here. This might be a little hard to see, so hopefully you can zoom in on that and see clearly. And we'll go ahead and work with number 5. Let's go ahead and simplify I to the 5th power. So if we continue with our examples, here. And it says, simplify. Number 1, we have, what do you do with I to the 5th power? Well, we'll say the highest multiple of 4 in I to the 5th power is just I to the 4th. And by my rules of exponents, I am left with 1. So I can break down I to the 5th into because my rules of exponents, I can break I to the 5th down to I to the 4th times I to the 1st power, and I replace this. This is equal to 1, and that's equal to I. So I just get the expression I out of all that. Okay. What if you had I to the 12th power? Okay, in this case, that's a perfect multiple of 4. So I to the 12th is just I to the 4 times I to the 4 times I to the 4. So this just equals, this is equivalent to what? Okay, so that's just equivalent to I to the 4 times 3. So it's a perfect multiple, and that just becomes the value of 1. If I go ahead and say, well, let me put this in, let's look at I to the 14th power. Let me go ahead and apply this highest multiple in something that will have leftover i's. So in this case, the highest multiple is 12, but I'm going to have 2 left over. So what I know is that I the 14th breaks down to I the 12th. That's the highest multiple of 4. And I multiply that by I squared, and that will be my leftover. Any multiple of 4 will always equal 1. So I the 20th, I the 24th, I the 28th, all these, any multiple of 4 always breaks down to 1 by our rules that we're using here. So this part's going to be 1, and this will be my leftover. And I have 1 times I squared, and I squared I want to reduce to a -1. So I just end up with a -1. I'll pull that. Okay. So you could do really huge numbers like I to the 113th power and reduce them to one of those key component values. Okay, let's do one more. Let's say we had I to the 39 power. The highest multiple of 4 here is 36, so I break that down to I to the 36th times I to the 3rd, and this becomes 1 times I to the 3rd, which is a negative I by our definition previously, because that's an I squared times an I, which is a -1 times an I, which is a negative I. And this whole thing reduces to negative I. And that's how you'd simplify some of the higher powers of I. Now let's go ahead and do some operations. We'll do some addition, subtraction, and multiplication, division. And then we'll call it a day. Okay, so operations. Operations with complex numbers. We're going to start with addition and subtraction. I might have to write this in blue. Looks like the black is fading out here. So the idea is just to combine like terms. So here, the main idea is to combine like parts, terms, just like we did with x's. So you combine the real number parts, and then you combine your imaginary number parts. Okay? And everything else is the same. So what we're going to do is we're going to go ahead and do a few examples. So you combine these parts together and always make sure you're simplifying. So I'm going to add and simplify if you need. Don't forget to do that part too as well. Okay, so here's some examples. And the directions might say add, subtract, and or simplify. So in a nutshell, if I have a problem that is, let's say, 4 plus 3i plus 2 minus I, what I would do in this case is, as before, I would remove my parentheses in case I have negatives. So I'm going to say 4 plus 3i plus 2 minus I. Remove all my parentheses, no changes in sign. And I'm going to add my real number parts together and my imaginary parts together. So in complex form, I'm going to end up with 4 plus 2 is 6, plus 3i minus I, which is plus 2i. And that is my final answer in complex number form. Not bad at all. Okay, so what if we have something like 5i minus 9 minus 5i can add a bunch of terms here. Well, the same thing applies. Let me go ahead and remove all my parentheses first. I have 5i minus 9 minus 5i minus 8 plus 2i. And what I'm going to do is combine all my like terms. I have 5i's minus 5i's, 0i's, and then plus 2i's. So I'll end up with 2i's. And here I have minus 9 and minus 8. So minus 9 and minus 8, I'm going to rewrite this starting with my real number part to keep it in complex form. Minus 9 and minus 8 is minus 17. And then what we have here is plus 2i. And that is in a plus bi form. Okay. One more problem, then we'll go to addition subtraction real quick. So I'm going to do one that has a bunch of roots in it. So as you can see, imaginary numbers are there, but they're called imaginary, even though we still work with them. Right? So there's plenty to do with imaginary numbers. Okay, let's see. Let's go ahead and do another problem I have here. Number 3. In fact, I'm just going to visit my worksheet real quick. Take a look at some other numbers. I'm going to do E on my worksheet. Let's go ahead, or D. Yes, so this is going to be from my worksheet. I'll leave some of the other ones as a challenge for you to do. Let's say we have negative 36 plus the square root of 20 minus the square root of negative 4. In a problem like this, we have to go ahead and do some simplification before we can even add or subtract these. So I can't add any complex parts because I have to simplify these first. So the first step is to recognize that the square root of negative 36 is negative 1 times 36. Simplify this. It doesn't have a negative, so it's just back to my basic rules for simplification. This becomes a 4 times 5. And this becomes a negative 1 times 4. Now, this is a perfect square, so I can bring that whole thing out and become 6. The square root of negative 1 is by definition I, so I have 6i. And then here I have plus 2 square roots of 5. And here, make my 5 a little clearer. And here I have 2i minus 2i. Okay, so this is what I have so far. Am I done? No, because I see that I have 2 imaginary parts that I can combine. And I have 1 real number part. So this real number has a square root in it, but it works the same way. I still want to write my real number part out in front, so I'm going to say 2 square roots of 5, and then 6i minus 2i is just plus 4i. And that is my final answer here. You can see I've done a lot of simplification from the original. And that's my A, this is A, even though it has a root in it, A plus BI form. Now let's go ahead and look at multiplying and dividing, the same idea. So let's look at multiplication and division. So again here, use the same rules. Apply your same multiplication and division rules. And then what you want to do, simplify. If need, after you apply your rules. Simplify if need, and that includes reduce higher powers of I. Now, one of the other things you have to be careful of is always simplify your roots first if you need to. as well. So there's a few tricks involved, and it's important to kind of work with what you have. If I'm multiplying and I do have negatives already in the square roots, they'll end up being a positive. Well, what you have to do is convert these first, and then you'll end up with I squareds and I cubes and I to the fourth powers. If you have a lot of i's, then you have to reduce those. So let me just start with a few key examples to get you started. And we'll start off simple and then work our way big here. Okay, so what we want to do is multiply slash divide slash simplify. Okay, so number one, let's say we have something like 2 times 6 plus 5i. Starting out with the basics. It works just like what we did with x's before. In this case, we'll have 2 times 6, which is 12. We'll distribute, and then 2 times 5i, we're just doubling 5i, so that's just 10i. And that is our final answer in complex form. Okay. Now, moving along from that, don't want to make this too long. Moving along from that, let's go ahead and add a 2i times 6 plus 5i. All right, let's add in that extra I and see how things get complicated here quickly. So in this case, we're just going to say 2i times 6, and then 2i times 5i. We have 12i plus 2i times 5i will give me 10i squared. Just like when you multiply an x times an x, you get an x squared. Well, the same goes with i's. Now, I have to simplify. I'm not done at this point. So here, I have a power of I that's greater than 1. I need to simplify that. So in this case, I'm going to go ahead and say 12i plus 10i squared would be plus 10 times a negative 1. I replace it by the definition of I squared when I broke down the 4 powers I that you want to know. I the first, I the second, I the third, and I the fourth. Okay, so what happens here, I now have negative 10 plus 12i, and this is my final answer in complex number form. That would be my final answer, a plus bi form. And I'm done. I always check to see if I have anything else I need to simplify. So again, the rule of thumb is to keep your answer as simple as possible. Okay, so we'll do a quick little FOIL problem. Let's do look at one on our worksheet. Let's do number G on your worksheet. Let's say we had 4 minus 3i, and we have 3 plus 3i. So again, we want to distribute all our values. We say 4 times 3 is 12. And then we have 4 times 3i, which is plus 12i. And then minus 3i times 3 is minus 9i. And then minus 3i times 3i is minus 9i again. So 9i squared. Okay, so minus 9i squared. So what I want to do is combine any like terms I have, reduce any higher powers of i's. This becomes 12. This is plus 3i minus 9 times negative 1. So now I know I can combine these two. The I squared comes back down to a real number, and I have 12 plus 9, which is 21 plus 3i. And that would be your final answer. So make sure you're able to get that. There's quite a few steps. And one more, last topic is if you had something you were multiplying that was like this. Okay. Now, if you were to multiply the roots together, you'd end up with -4 times -12, which is +48, which is not what you're going to get here. You've got to be careful. I'm going to put a little star here. You have to first convert to i's. Okay? These are negatives under square roots. So they don't negate each other and give you a real number. That's not how it works. What you first have to do is convert this to a 2i times a -1 times 4 times 3. So this becomes 2i times a 2i square root of 3. So this is definitely not the same thing as a +48. What you're going to end up with here is 2i times 2i, which is 4i squared, the square root of 3. And the 4i squared will give you 4 times -1, which is -4 square roots of 3 as your final answer. So if you write that in a plus bi form again, you would say -4 square root of 3 plus 0i. Okay? But that's sufficient. So be careful of some of those types of problems. They're a little tricky. You have to make sure you convert first. Okay, the last little bit here, and then we're finally done. This is the long video. But we've managed to put a lot of complex number operation basics all together here. Of course, you could always watch this in chunks at home. Let's go ahead and look at division and complex conjugates. What we really do here is we don't really divide by i's. We get rid of i's from the denominator. Okay, so the idea is if you're dividing by I to any n power in the denominator, you want to eliminate and simplify via your complex conjugate, which we introduced earlier. Okay. So here's an example. And we'll follow with more examples. And typical problem would say simplify, divide maybe, all the same. Okay, so what we're going to do is we're going to start out with an example that has 1/3i. And you might say, well, that seems like an okay answer to leave, but no, we want to get rid of i's from the denominator just like with square roots. So the complex conjugate, if you remember, is if you have a plus bi, the conjugate would be a minus bi. Okay, that's my CC. In this case, I don't have a real number part, that's just 0. So the complex conjugate here is just minus 3i. So what we have is 0 plus 3i. This becomes 0 minus 3i. So all we need to do is multiply by minus 3i, and we'll notice that you can really just multiply by 3i and get rid of your I squared. So I'm going to go ahead and multiply this by 1/3i times 3i/3i. And we know that what we have to do is multiply numerators and denominators to keep the value the same. So if you're going to multiply the denominator by your conjugate, you've got to multiply the numerator as well. So the first step is to find this complex conjugate, and then your second step is to multiply numerator and denominator by it to eliminate the i's. those are our two steps. So once we find that complex conjugate, multiply numerator and denominator by it, and now we go ahead and simplify. Let's say 3i over 9i squared is what I'm left with. And I'm going to have to move over here, give myself a little more room. So if I have 3i over 9i squared, I will reduce this down to, I'll replace this with the value I know it to be, 3i over 9 times negative 1, and this becomes 3i over negative 9, which is just negative I over 3. And that's an appropriate reduced form of this 1 over 3i, an appropriate answer. Now another trick here is to note, when you don't have a real number part, you can use positive 3i or negative 3i to get rid of it. So one note, if just have a bi term in the denominator, you can multiply to multiply. You don't have to do the negative. So, for example, just a little variation on this problem, if you had 1 over 3i, I could just multiply by 3i, or actually I could just multiply by I over I. So if I have a bi term in the denominator, you can use that to multiply, or just, or just I. Some ways you could cut corners here. Okay, so I could just multiply by I over I, and then I have I over 3i squared, and that becomes I over negative 3, which is the same thing. It really eliminates a lot of steps, but if you're unsure, just remember that the complex conjugate always works. Okay, so a little trick there. There's a lot of little tricks. As long as you're using the rules of math correctly, it's okay to do. But if you're not, you're in trouble. So 2, let's go ahead and use one that has a fraction. Let's say I had a 4 over square root of negative 20. Okay, how would I reduce that and simplify that? I would do 4 over, convert this to my I form. This becomes negative 1 times 4 times 5. This comes out, becomes an I. This comes out, becomes a 2. So I have the expression 4 over 2i square roots of 5. Okay, now I have an I and a square root mixed together. I have to get rid of both of those. So what I'm going to do is, firstly, give myself a lot of room. 2i square root of 5. I need to get rid of my i's and my square root. So I can multiply by I, top and bottom, as my shortcut, and the square root of 5, top and bottom. So what I'm going to do is I'm going to multiply by I square roots of 5, I square roots of 5. And the main idea to figure out what you're going to multiply by is to think of what you need to get rid of the i's, what you need to get rid of the square roots. Here, an I times an I will give me an I squared, which will bring it to a real number. That's good. A square root of 5 times the square root of 5 will eliminate the square root, and that's good. So altogether, what I'm going to have is 4 times I square root of 5 in the numerator, and in the denominator, I'm going to have 2I times the I in the front times square root of 5 squared. There's a lot of stuff here. I made a little bit of a jump from the last problem. But this covers a lot of the essential ideas involved. Now altogether in my numerator I have 4i square root of 5. In the denominator I have 2i squared times 5. And then one more last step here. One or two more, depending upon what you need, is what we have is 4i square root of 5, numerator looks good, over 2 times negative 1 is negative 2 times 5, we have negative 10. Okay, and then I'm going to reduce this just by a bit. 4 tenths can be reduced to 2/5. And I can bring my negative to the top or out in front. And that will be my final answer. There's a lot of steps. This is a good problem because it involves a lot of principles we've been working with. Simplifying radicals, complex numbers and rationalizing, and using complex conjugates or eliminating i's from the denominator. So many principles involved. This is a good problem to practice. Okay, I will do one more from your worksheet that involves a little different conjugate, and then I think we're in good shape to tackle some complex number operations and simplifying some of those problems. Okay, let's do this from the worksheet. Number 3 is, let's see if I do a variation. From the worksheet, 3 over 2 minus 3i. And that does look like a good one to practice. Okay, here I'm going to have to use the formal definition of complex conjugates. No cutting corners really in this case. What I'm going to do is first look for my complex conjugate. I'm going to do C for short here. My complex conjugate of 2 minus 3i should be 2 plus 3i. So that means I want to multiply numerator and denominator by that. So I'm going to say 3 times 2 plus 3i over 2 minus 3i times 2 plus 3i. This will ensure that I get rid of all my i's in the denominator, and I can reduce and work with this. This becomes 3 times 2 is 6, 3 times 3i is plus 9i, and this is all over 4 plus 6i minus 6i minus 9i squared. Okay. Now what I have is 6 plus 9i. The numerator is simplified, so I look to simplify the numerator, and then I separately want to simplify the denominator, which in this case, luckily for me, this is the whole idea with complex conjugates, and the plus and minus sign, the opposite sign in between, eliminates a lot of your middle terms. So now I just have 4 minus 9i squared, and that becomes negative 9 times a negative 1. So this now becomes 6 plus 9i, 4 minus 9 times negative 1, and then we have 6 plus 9i over 4 plus 9, and then over here we have 6 plus 9i over 4 plus 9, which is 13. Okay, that's our final answer, but in complex number form, I have to separate my real number term from my complex number part, or my real number part from my complex number. So this is not complex number form. Oh, my red is running out too. All right. So your markers, when your markers start running out and your coffee starts running out, it's time to wrap it up. So our final answer here will be, this is the same thing as 6 over 13, and I can see that simplified, reduced, that's great, plus 9 over 13i. And I separate these, because these are two different fractions, into my a, my real number part, and bi, my complex, my imaginary part, all together, which makes my complex number form. And that would be your final answer. And that's it for now. Practice as always. There's a whole variety of problems to do out here based on these basic principles. Thank you. Until next time.